Good evening to all of you. The topic of this presentation is optimal PMU placement for performance monitoring of renewable energy plants. More specifically, LVRT performance monitoring or HVRT performance monitoring. That's the focus of this study that we have done at IIT Bombay. The background is actually once we are done with the other speakers which mentioned about testing and certification procedures for these renewable energy power plants. So this study is actually beyond that, means once that certification and testing is done and the plant is already operating in the system, how we can actually monitor the performance of the plant to see whether it is really complying with the regulations in place or not. So that is the background of this study. In some of in the major power plants, renewable energy plants, we may have access to the measurement. So during an event in the grid, we may actually look back at that data, measurement data, and check whether the renewable energy plant has really complied with the grid code in place or not. But that's not the case with all the plants that we have in the grid. So there will be number of renewable energy plants, particularly small units, which we may not have access. Actually, we may not have full visibility of those units. So that is the question. The question is coming: how we can actually monitor the performance of grid code compliance of these renewable energy plants. So in this study, what we try to do is we try to use the application of these PMUs, phasor measurement units, to utilize that and try to assess the compliance of these renewable energy plants for a given plant, taking the measurement of the PMUs that we have in place at high voltage transmission level generally. So this is basically estimating the performance monitoring of renewable energy plants. So we already heard about this, I think, LVRT. I will not touch more the LVRT requirement, but I'll little bit add to this. There are primarily, we can divide this LVRT requirement into two categories. One is reactive power priority LVRT, and the second is active power priority LVRT. So what does it mean? Actually, during a voltage dip, during a fault-induced voltage dip in a power system, when the renewable energy plant sees the voltage dip, what it should actually give priority to, because it can give priority to active power, it can give priority to reactive power. Now, most of the grid operators, most of the system regulators or countries actually demand reactive power priority during the LVRT. What does it mean is, there is a voltage dip, let the plant actually inject more reactive power to the grid so that there is a quick recovery of the voltage and the grid comes back to a steady state operating point. But what is happening when there is a voltage dip? There are two aspects that we have to look at. One is voltage is getting down in the system, and second is active power generation is falling down because of active power generation from the renewable energy plant, which sees this voltage dip. Now we have two aspects. For voltage recovery, we need reactive power, more reactive power at the transmission level. For active power recovery, for frequency stability, we need more active power actually. So what does it mean? If a grid is having frequency as a more concern, then it might actually prefer to give priority to active power during voltage dip, such that, because particularly in wind plants, during the voltage dip, when power goes down during the fault, it takes some time to come back. It's not like conventional power plants will instantly come back after the fault is cleared. So therefore, when the fault is cleared, during the active power recovery, there is a potential of further frequency dip, which might actually be because of shortfall of generation after fault clearance, because the generation from renewable energy plant is ramping up slowly compared to the conventional power plants, while as load will quickly come up. So therefore, there is a potential of having shortfall in generation as a whole in the grid, and which might potentially affect the frequency. That is the reason some of the countries, which is primarily the small power systems, small grids, actually prefer to give priority to active power injection during the fault or during this LVRT period. One of the example is Ireland. There you have to actually give priority to the active power during the fault, while as in most of the countries we have a reactive power priority. Similarly, in Indian electricity grid code, again the grid code was mentioning keeping this CEA recent amendment aside, the previous grid code, which is actually still in place, CRC grid code, it is mentioning that the active power should be in proportion to the retained voltage, which indirectly, in most of the cases, means you have to give priority to the active power. Basically, the control you have with the renewable energy plant with this power electronic interface plants is you have control over current actually. That's what will be dictated. So therefore, to maintain that proportionality with the retained voltage of the active power, you actually have to give more priority to active current such that there is that proportionally maintained. But now that is, I think, particularly in the context of CEA, these recent regulations, it is clearly mentioning that reactive power should be given first priority rather than active power. I think this, I probably need not to give too much attention because we already have seen other speakers speaking about this. There are different ways of, this alveolity testing requirements are required. And I would like to little bit mention about this model based. So there is also, apart from this testing, model of the renewable energy plant is also required, which is particularly required for certification purpose. For example, in India, there is a concept of self-certification because of several reasons. One is this testing procedure is time consuming. So therefore, you have an option of self-certification where you give the model, validated model to MNRE through NEWA, and they can check the model and check whether it is complying with the grid code regulation of India or not, and accordingly, and they will have a self-certification which is valid for a certain period, I think around 1 year, and then by that time the testing has to be done and shown accordingly. What are the limitations of monitoring performance, LVRT performance monitoring during the operation is, and what are the other reasons? For example, the power plant renewable energy plant has undergone some maintenance or some changes. There has been some retrofitting done in it. So how to ensure that it is now again complying with this LVRT or any grid code in place? And then a difficulty in monitoring already I mentioned. So there's a whole this bigger question how we can at least monitor whether the renewable energy plants are complying with the grid code or not. Then the next question would be how to enforce that compliance if there is any deviation in that. What we try to do is we have these PMUs, phasor measurement units, which actually are measuring the phasors of voltage and currents at each substation wherever they are placed. And you can have precise, you can have one is fast dynamic data. It has higher sample rate compared to conventional measurement devices that we have had in place before these PMUs came up. So therefore, this PMU data, which we have measurement available from the PMUs, we could potentially use that measurement as a resource to assess the monitoring, this performance monitoring of these renewable energy plants. I think we most of us would be already familiar with that Indian grid is having huge project for this wide area measurement system. Number of PMUs are being placed, have been already placed and are being placed in the power system primarily at higher voltage level, 220 kV and 400 kV and all that. So this is the current status to a reasonable extent that we have complied as of now. So if you see here, number of PMUs proposed are around 1670 roughly, and we have number of PMUs already installed there, and remaining are actually being done. So there are already, what we actually tried to, there are already number of PMUs in place in the grid. Can we try to use those PMUs to have these performance monitoring of this? So what we tried to come up with a proposal that we can do an optimal PMU placement for this performance monitoring, considering the existing PMUs that we have already in the system. So which essentially might mean that in some of the cases we may need to have additional PMUs to be placed at strategic locations to have this performance monitoring of all the renewable energy plants in the system. So that's what we try to do here. This is one of the methodologies. There are different methodologies which we can use for optimal PMU placement. We have used this binary particle swarm optimization. The other challenge that we saw while dealing with this is that how to have, so we have number of these renewable energy plants in the grid at different voltage levels, for example, depending on the capacity. So how to actually now monitor the performance of these units with these PMUs. So what we realized is it might be practically very difficult to monitor the performance of each and every unit individually, given the infrastructure we have in place as of today. So what we try to do is, can we, instead of monitoring performance of this LVRT performance at each and every individual unit, can we monitor this performance at pooling station? So if we have a performance monitoring at pooling station or aggregation at aggregate bus, we can potentially have an idea whether this region, this pooling station is actually complying with the grid code regulation or not. So there's the idea of clustering these renewable energy plants at one particular substation. And we came up with a method to actually aggregate these renewable energy plants at some of the substations and try to then assess the monitoring of those plants, those aggregate these pooling stations. So this is the approach that we adopted to cluster these multiple renewable energy plants, be it solar PV plant or wind power plant, at a pooling station, substation, and then try to monitor the performance of the entire cluster. So this is the validation of clustering process that we actually adopted. We are comparing the results of a cluster-based approach and the results of the actual detailed model, which are pretty close as per these measurements. In our case study, we took Gujarat grid and we modeled it from 765 to 132 kV level, and accordingly we placed the clusters of these renewable energy plants at different substations. In one of the approach we used the clustering that I already stated, and in other case we actually tried to have a reduced equivalent model of the grid, maintaining some of the original buses in the system where we will have PMUs, so that we can use that PMU measurements from the field and use that to estimate the performance monitoring of these renewable energy plants. These are some of the results that we have of these PMUs, PMU requirement for these performance monitoring of the renewable energy plants. In method one, where we used the clustering approach. We have a requirement of additional 22 PMUs, if you see here in this case. So in other one more as a research study, we considered one more scenario where we don't have any existing PMUs. There we need actually 32 PMUs. So if you see the first row, 71 is because most of them are already existing, and we need some additional to actually have full monitoring of all the renewable energy plants. Similarly, if you see the next one, where we used the reduction technique, we actually retained only those buses where we have PMUs in the system, and remaining grid, we actually reduce it to lesser number of substations, which actually help us to easily assess the performance monitoring of these renewable energy plants. If you compare the two tables, there is less number of PMU requirement in the second case, where we are using the reduction approach compared to the first, where we don't use the reduction approach. So concluding the presentation, we try to focus on how we can monitor the LVRT, in general grid code performance of these renewable energy plants in the system, and what could be the potential approach? Can we tap the existing PMUs that we have in place and try to utilize the measurements that we get from those PMUs to actually assess the and monitor the performance, LVRT performance monitoring or grid core performance monitoring of these renewable energy plants? We have had additional results actually, or the validation results, which are not part of this presentation because of the time that we have for the presentation. But the whole idea is to actually use the existing PMUs to monitor these renewable energy plant performance, LVRT or grid core performance monitoring. Thank you very much.